How well can we navigate? At the end of this presentation, you should be able to define navigation performance indicators, to list requirements for various navigation modes, to identify limiting factors, and to describe methods to improve performance. Let us go over a list of 7 performance indicators. Uncertainty refers to the predictable accuracy at a certain confidence level. Usually, we work with 67%, 95%, 99%, but that is dependent upon specifications. Reliability is the percentage of time a particular system delivers the specified accuracy, and that would include downtime, equipment, and environment. Coverage is the region for which over which the system provides the specified accuracy. The region here we can think in terms of 2 dimensions or 3 dimensions, and the accuracy will be in terms of the geometry, the signal power, receiver sensitivity, atmospheric noise. So all these, all that will affect accuracy. Capacity is the number of users that can use the system. In other words, there is going to be a limit of users. That's the capacity. More than that, the system becomes saturated. Fixed rate is the shortest fixed interval. And for example, 1 fix per day, 10 hertz, 1 fix per second, etc. Fixed dimension is the dimension of the positioning. You should recall that we define fix as a synonym of positioning, and that's in the jargon of navigation. So is the system capable of 2-dimensional or 3-dimensional positioning? And there is the cost to establish and maintain the user. And we may think in terms of also the cost to the user. So if a enterprise establishes and maintains a system, this enterprise may charge a fee for users to use the system. Here we have 4 types of position uncertainty specifications. Predictability is the uncertainty of positions within a well-defined reference system, usually as a function of space and time. Repeatability is the accuracy of return to the same location, and it can be specified within a certain time period, temporal validity. Relative uncertainty, it may have 2 meanings. It may be the accuracy of positions with respect to a co-observer, or the accuracy of positions with respect to the immediate previous positions of the same object. And finally, resolution can be the system noise level and the system readout limit. So the resolution would be a limit that a limit for the accuracy. In kinematic positioning, we are limited in terms of redundancy. What is a redundancy? Redundancy is well, we have defined redundancy. Redundancy allows reliability to be monitored, because we may have several measurements or several estimates, and they can be compared with each other. In static positioning, we can obtain redundancy in two different ways. There is a temporal redundancy and there is a spatial redundancy. The temporal redundancy is when we measure over and over again. The spatial redundancy is when we add new measurements. So, for example, we are measuring the temporal redundancy would be, say, we're measuring from A to B, and this measurement is repeated over and over again. Again, both points are stationary. And the spatial redundancy is we add a point C, now we measure from A to B and from C to B. In kinematic positioning, we don't have the luxury of temporal redundancy, only spatial redundancy. In other words, we would require more instruments. Therefore, it implies increase in cost. So that's why I say here it's costly. We need to add more base stations. The alternative in kinematic positioning, I mean, it's valid for static as well, is a careful error analysis, repeated calibrations, and frequent reference position checks. So careful error analysis in the sense that the system will have to have checks, internal checks, to validate their measurements and their estimates. Repeated calibrations means that the instruments should be calibrated continuously, frequently, in such a way that we know about their performance, the capability, and reference position checks. These would be, for example, if we are, we may cross the passages. So if we are making surveys that go in parallel lines vertically, we may add some lines that go horizontally, crossing the vertical lines. So the intersection of these lines would serve as position checks. Now here we have the concept of position fix. There is always uncertainty. There is always uncertainty in any measure. But when we have a fix that is derived from the crossing of two lines of position, we have these the upper figure, we have this first point S1, the distance is defining the circle is the line of position 1, which means that the vessel could be anywhere along the red line. And we have this station S2, which is defining a new line of position 2, and we have they intersecting at this point R. So the thing is that these distances measured from S1 S2, they may have an uncertainty associated with it, of course, but the fix is unique. Okay, the fix is where these two lines intersect. Now, if we have a situation in which we have, for example, 3 lines of position, now we have a line of position 1 in red, line of position 2 in green, and we're adding this third line of position in blue. The advantage is that we are adding redundancy. So what becomes clear here is that we have potentially 3 fixes. Which one is the correct? Well, there is a inconsistency in here, but that's actually an advantage in terms of redundancy, in terms of quality control. So we can say that the fix is not uniquely defined. Now we have the uncertainty associated with measurements. So going back to the situation in which we have these 2 lines of position, we can think that we have the measurement and we have the uncertainty. So we have these the crossing of the line of position, and then these 2 lines that are between the line of position in red and in green, that they represent the uncertainty, the variation, the standard deviation of the measure, the distance. So the geometric representation, the geometric shape that we have is a diamond. So we call that a diamond of error. If we have more lines of position, so we're adding redundancy, we can actually compute the error ellipse. So the error ellipse is indicated in black. So the error ellipse would be then a region in which the fix could be anywhere. And of course, in the diamond of error, also the position fix could be anywhere in there. Sources of uncertainty: bias, which represents an offset from the true position, and that affects both line of position and the sphere of position. And why such a offset may happen? Well, mis-synchronization, delays, say atmospheric delays, wrong reference coordinates. We have the rate, in which case the error associated with line of position and the sphere of position grows with time. We have refraction. There are 2 types of refraction. Refraction dealing with speed and refraction dealing with profile. The speed, the error grows with distance from the reference. In the profile, the error depends on refraction or spatial changes. Signal noise, they reflect random errors in the line of position and the sphere of position. Interference, when the noise is so great that the signal cannot be tracked, it cannot be observed. And multipath, which is a geometric dependent noise-like error that affects line of position and sphere positions. There is a very good reference that is issued by the U.S. Federal Radio Navigation Plan that it basically defines navigation requirements for civil users of in the U.S. for navigation services. So it deals with management policy. So that's called the Radio Navigation Plan, and there is one also that deals with the systems. It's more descriptive and very good, usually very good. It's called the Federal Radio Navigation Systems. So we have the link there if you were interested in having the document. How do you overcome limitations? We have to select the appropriate system. We have to design the system deployment in such a way that has a favorable geometry. We have to install the antennas in such a way that they minimize the location, minimize multipath. We have to calibrate systems. We may have redundancy to detect evidence of errors, and one such a system is the receiver autonomous integrity monitoring. And last but not least, we should rule the first rule of navigation of never depend upon one system. If you have two systems, if one breaks, we have another one. If we use only one system, if that breaks, we have nothing. As a summary, accuracy is only one of several navigation performance indicators. Navigation requirements vary considerably among applications. Many factors may limit navigation performance. Most limitations can be overcome by appropriate design and operation. And the first rule of navigation that we should keep in mind is never depend on one system.